Okay, so now we're going to tackle the situation where we need to apply the chain rule more than once. So what we said here, sometimes when we apply the chain rule, the inside function still contains a composition. So it's basically like a composition of three functions. And that means when we take the derivative of the inside, we're going to need to apply the chain rule again. Okay. So let's just take a look at the difference between those things. So on the left side here, I have y equals cosine squared of x. So that's the same as y equals cosine x squared. Okay, what's the inside function here? It's just cosine x. The outside being u squared. So cosine x is not a composite function. This is just our normal chain rule as we've done already. However, let's look at the next one. And again, I'm going to rewrite this as cosine of the square root of x squared. So now my inside is cosine of root x, and my outside is still u squared. So do you see how this inside function, if I were to go take the derivative of this, I have another inside function. I have cosine of something that's not just x. It has its own derivative. So this is where, when we would go to do this, we would need to apply the chain rule again. And that's our first problem. So let's go ahead and do it. We just kind of wrote it out, but I'll write it one more time. Okay, so our y prime will start by doing the derivative of the outside, which will be 2u. Okay, we know what that u is. It's the cosine of the square root of x. But here is where, when I multiply by the derivative, this has its own inside and outside. So the outside is cosine u, and the inside is the square root of x, or x to the 1/2. So when I'm going to multiply by the derivative of cosine of root x, I'm going to apply the chain rule. I'll have negative sine of root x, so derivative of the outside, leaving the inside, times, I guess I should have put that like this, the derivative of the square root of x. Which at this point you may have gotten to the point where you're memorizing it as 1 over 2 root x, or 1/2 x to the negative 1/2. It's the same thing. Okay, so then we're going to, sorry, that was a little strange. My screen freaked out on me for a second. We're just going to do some cleanup. I see 2's are going to cancel. And it looks like I really just have negative sine root x, cosine root x, all over root x. Looks good to me. Okay, so there's one more example of this. Actually, I think there's even a couple more on the next page. There is. Okay, so what I'm going to do is walk you through one more, and then I'll have you try the next two after that. So let's do inside, outside. Once again, we have an e to a power. So that always results in e to the u being the outside. And then, excuse me, the inside being the power. Now, do you see, once again, how this is a composite function? So we're going to need a separate inside-outside for that. I usually kind of start my derivative first, but you could do both inside-outsides if you want to. So it's going to be e to the power. And then we got to multiply by the derivative of that power. So inside here is x squared plus 1. Outside is square root of x, or x to the 1/2. So when I start the derivative of this, I'm going to start with the derivative of the square root. Should have written as the square root of u. Okay. The derivative of the square root of u is 1/2 u to the negative 1/2. Leave my inside alone, and then multiply by the derivative of the inside. All right, again, now I'm just doing the cleanup. It looks like I have an x e to a root x squared plus 1 all over a root x squared plus 1. Okay, so try on the next page. There are 2 more problems to try. This is kind of getting to that point in the chain rule where these are as tough as they're going to come. Okay. So pause the video and see what you can make of it. All right, how'd it go? Let's start with number 3. I have a square root of u as my outside, e to the x squared plus 1 as my inside, which clearly has its own inside outside, right? It's an e to a power, so the outside would be e to the power, e to the u, the inside would be the power. So I'm going to approach this. I need to take its derivative. I'll start with the derivative of the outside, which will be 1/2 u to the negative 1/2. So 1/2 u, the inside doesn't change, to the negative 1/2. And we're going to multiply by the derivative of the inside, which is e to the power times the derivative of the power. And then just a little bit of cleanup. And when I get to number 4, I see that I immediately have a product. I have x cubed times sine squared. So I'm going to start with a product rule here. X cubed, oh. Sorry about that. I realized that I had not finished my product rule, so I did that. Let's try that again. So I have a product. I'm going to have x cubed times the derivative. All of this is the derivative of sine squared, which we'll talk about in just a second, plus sine squared times the derivative of x cubed, which is right here. That does not require a chain rule. So everything in this first line that's in the black writing is just straight product rule stuff. It's when we get to the derivative of sine squared of 5x that we need a chain rule. Inside would be sine of 5x, outside would be u squared. So the derivative will be 2u. And then I need the derivative to multiply by the derivative of sine of 5x. So I'm doing this one in my head. Sine of 5x. So the outside would be sine, so the derivative would be cosine. And then I'm going to multiply by the derivative of the 5x, which is just 5. So the goal is that you eventually get to the point where you don't necessarily have to write down inside and outside anymore. And if you're already there, that's awesome. It's easiest to do on problems like this where the inside is just like a 5x or a 3x because it's a pretty straightforward derivative. So that's where we're headed, is to be able to do these chain rules in our head. Then I have the rest of my product rule, and I just did a little bit of cleanup. Not a lot more going on with that one to simplify. Okay, so we actually use the chain rule to find the derivative of exponential functions. And we're going to do this by using a kind of a clever way to rewrite the function first, and then we'll be able to apply the chain rule. So the goal is to find the derivative of b to the x, where b is a positive number not equal to 1. So we know that if b is e, the derivative of e to the x is already just e to the x. So now we're going to prove what the derivative is for any b. So here's the rewrite that is kind of cool. B to the x is equal to e to the ln of b to the x, right? And that's because, as we know, e to the ln of b is just equal to b. So I'm substituting the b with something that's equal to b. Okay? And it's not clear exactly why I'm doing that at the moment, but it's going to help us use the chain rule. So then when I go to do the derivative of b to the x, I'm going to substitute in e to the ln of b to the x. And then our rules of exponents tell us that when you have a power to a power, what do you do with those? You multiply them. So this is equal to the derivative of e to the x ln of b. And here's where we're going to apply the chain rule. So to this thing right here, it's e to a power. So our outside is e to that power, and the inside is just that power. So let's take that derivative. Derivative of the outside, derivative of e to a power is just e to that power. And then I'm going to multiply by the derivative of the inside. What's the derivative of x times ln b? Remember that ln b is just a constant. B is a constant. The natural log of a constant is another constant. So this is really like the derivative of 3x, right? It's just the constant. So ln of b. But keep in mind, remember we made this clever substitution? E to the ln b, or e to the x ln b is really equal to e to the ln b to the x, which is really just b to the x. So this right here is just b to the x. And there we have a formula for the derivative of b to the x. So the derivative of b to the x is that b to the x times the ln of b. And you'll notice that if b is e, it would be e to the x times the ln of e. And what is the ln of e? Oh, it's 1. So it would just be e to the x. So you don't have to have this process memorized or anything like that. I'm hoping that you can follow it because, again, one of the goals of this class is to expose you to that mathematical logic, but I'm not going to require you to be able to reproduce it. But what you will need to have in your list of things that you've memorized, basically, is the formula for that derivative. And just a real quick set of problems using this. I mean, straightforward application. If you're trying to find a derivative of 2 to the x, it would be 2 to the x times the ln of 2. So that's straightforward. Or you might see this in, say, a product rule. So when you're going to apply the product rule, you would take that derivative as 4 to the x times the ln of 4. I mean, there's nothing new or special necessarily about it, but I just wanted you to see a couple problems of that in action.